Welcome everyone to the Thursday EasyPower webinar. My name is Jim Chastain. I'm with the applications group here at EasyPower, and welcome to our last webinar for the year. Before I introduce our guest speaker today, as we usually do, I'd like to get some feedback from the audience, as much in helping guide the discussion today as to help understand kind of the perspective that people are coming at the subject matter. So I ask for your participation in our poll questions. We have 3 of them today, and clearly no obligation on your part, but we would appreciate the feedback. So the first question is, what maintenance standard do you currently follow within your organization? If you would just indicate by selecting one. We do appreciate the feedback. So here's how everyone's kind of voting in on this one. Looks like for the most part people are following NFPA 70B. Sounds good. Let's try the second question. And that is, in your opinion, what's most likely cause of arc flash incidents? And here's how people have chimed in on this one. And not really surprised by the expectation here. And then our final question is relates to your appreciation or understanding of what the potential cost could be of an arc flash accident. Just wondering if people have an appreciation for what the magnitude is. So let's give this another 5 seconds. And here's how people have chimed in on this one. And we do thank you for participating. And so now I'd like to introduce our speaker for the day, Mr. Lee Marchesal with Workplace Safety Solutions. Lee, I'll hand it over to you.
Okay, very good. Good afternoon, everyone. Thanks for taking the time to attend this webinar. This is a real important subject. I've spoken on a number of occasions for national conventions on this because I think it really is an important part of our jobs, and it's often a challenge to get this maintenance that we need to do, get it done. So we'll get right into it. So here's the objectives of what we're going to be hoping to cover today. We're going to kind of go into the basics of arc flash and arc flash. I know that it's elementary for a lot of you folks out there because you have a good understanding of this, but it's important to cover this just to get the background of the other parts that we're going to be talking about through the program. We'll talk about cause and effects of the arc flash incidences. We'll talk about the importance of conducting engineering arc flash studies versus necessarily going beyond maybe the table method in NFPA 70E, and talk about some of the differences there. We'll talk about why maintenance is so important, and we'll get into some of the consequences of lack of maintenance, including outage time and also, more seriously, legal issues and injuries. We'll talk about mitigation methods in brief, just to see what we can do to get some of these things down. So some of the reference standard, everything sort of started with NFPA 70. That's the National Electric Code, and you know, OSHA rules, and everything started back then. I mean, NFPA 70 has been around for well over 100 years, and so it's a design standard. It's not a safety standard per se. It's a design standard. It's helped, you know, originally designed to keep fires down. From that information, we've gotten a lot more, including 70B was developed beyond NFPA 70, and then 70E, of course, came in the mid 70s based on a request from OSHA to come up with their standards. Then from that, of course, we got the OSHA Subpart S 269 standards in general industry, and Subpart K and Subpart B in the construction industry. And then we also have the National Electric Safety Code, which is IEEE C2, ANSI C2 document, which will cover more of the utility and medium voltage or utility-like work. A lot of people think, well, it is just utilities, but it's not. It's medium voltage. It's utility-like work. So that's important to make that distinction as well. And then there's the National Electric Safety Code 1584, which has just been revised, and EasyPower will be getting that information out to everyone that has that software and uses that software. There's some pretty significant changes, and you could talk to them about that going forward. All right, a little bit on arc flash stuff. So first off, what causes an arc flash? I've heard people say, geez, if a mouse gets into the switchgear or something. Well, if a mouse gets into the switchgear, it's not a real high resistance fault. It's a lower resistance fault, so it's going to cause heat, it's going to cause maybe fire, certainly kill the mouse, but it may not cause, depending on the voltage and so forth, and the proximity to whatever it's working with and the load, it may not cause an arc flash in itself, just do some other damage. But generally, it's from a very low resistance fault that has occurred from a short circuit or ground fault. So generally, it could be tools or it could be failure of equipment. Whenever you have moving parts within an equipment and you move those parts within the exposed energized parts, you have the risk of causing a contact, which will cause a ground fault or a short circuit. And that's the kind of thing that we have to take care of based on maintenance. And so that's important. So a little bit more on arc flash stuff. It reaches the surface of the sun about, temperature of 35,000 degrees. Anybody that's an electrician and has worked with tools knows that, if you get a screwdriver or you cut into a Romex or things like that, it melts that hardened steel instantaneously and blows it away, and it's gone, and you've got a damaged tool. So one thing to think about is, if it's 120 volts, that's probably all you're going to see is that little spark and that little damaged tool. But if you get to 277, now there's enough pressure, enough voltage to cause the electrons to be displaced in the atoms of the air, and that's ionization, and that can cause a plasma effect to take a single-phase fault, a ground fault, and turn it into a three-phase fault. So it becomes a lot more serious when you get into 277, 480 volts versus 120, 208. Not to say that a 208 fault can't do that. It's not likely to do that. I mean, it's not likely to go from a ground fault to a three-phase short circuit. We have copper vapors that expand 67,000 times. One of the things to think about is we may have an arc flash boundary somewhere out in here, and what will happen is, this arc flash at that point will be from a first degree to a second degree burn. However, one thing to think about is you still have molten metal, and if your risk assessment says that those molten metal is outside the arc flash boundary, so I don't need a shield. Well, you may want to consider a shield anyways, because even though it's not going to burn your face off, there's still molten metal, and it could cause pits in your face and so forth. So might want to try to avoid that. And with that, of course, hot air expansion and all that. And then you also have intense light, and the intense light can cause some retina damage. So that's why we have tinted shields. They are now gray tinted shields, so they don't distort colors. And it's important to know colors when you're doing electrical work, because you should be able to differentiate what's green and what's brown and what's red, and those similar kinds of colors under a green tint may be confusing. So with the newer light gray tint, it takes care of that color issue. So that's an important thing to think about. We could have sound waves and pressure waves. And the noise level from an arc flash depends on the significance of the arc flash. How big of an arc flash event is it? How much heat was there? It's similar to thunder and lightning. The larger the arc flash, the larger the bang, and that's important to think about. So there's a couple of things we have to know. First off, we have to know what our arc flash boundary is, and we have to know what our arc flash hazard is at our working distance. Typically for working distance, we're talking about 18 inches for 480 volts and below. When you get into medium voltage, then you go into 36 inches because that's where you're going to be required to use a hot stick to do the work to verify things are de-energized. So let's start by talking about the arc flash boundary. So the arc flash boundary is this area back here, and it's the point at which the arc flash will drop to 1.2 calories per square centimeter. So calories per square centimeter is the measure of this incident energy. And so outside the boundary, you may have a first degree burn that may cause like a sunburn. And that's fine, and as long as you're outside that boundary, you don't need to have any further particular equipment for arc flash. Once you go inside the arc flash boundary, now you have the potential to get a different kind of a burn. And this would be a second degree burn where it starts to blister up. And that's an important thing, an important distinction to know. It's part of what a qualified worker must know is where is that boundary. If it exceeds the shock boundary, which is the limited approach boundary, there's two of those boundaries, limited approach, restricted approach. For the limited approach means how close can a non-qualified worker get before they can't go any further. And for 480 volts, it's 42 inches. If the arc flash boundary exceeds that, then the boundary needs to go back to that arc flash boundary. And we're going to have some examples of actual arc flash studies where that boundary is exceeding it. So then we have to figure out, well, what is the actual the cause, and what are the things that contribute to the level of the arc flash? So first off, the available voltage fault current. So that could be dependent on the size of the transformer that's feeding it. It could be dependent on the utility that's feeding that transformer, and those kinds of things need to be determined to figure out as part of the assessment. And then the clearing time. What is the clearing time from the device that's protecting your work area? And that, of course, depends on the time current curve of the protective device that you're dealing with. So incident energy levels are directly proportional to clearing time, because the longer the time it takes to clear, the more and further out the arc flash will go. And so that's an important part of a risk assessment that a qualified worker needs to understand before he gets started on this. Now, hopefully there's been a study, so all that's been done for him, and he can look at the label and determine what his PPE is based on the information on the label. The other part that's important is, what is the impedance from that protective device? So if you are working on the main switch and it's the main bus feeding, it's just being fed from the transformer, the utility transformer, what's giving you the protection? So there really isn't a whole lot of protection, because you feed it through the impedance of the transformer, and then you go up to the fuse feeding the transformer, and that may blow quickly if you have a fault on the conductors going to the transformer from the utility. So it gives protection for that, but it doesn't give you a lot of protection downstream from that. So the arc flash level is going to be very high, and your time, because of the time element, it's going to take a lot of time to read through that impedance. And the other example is, if you're feeding, say, a disconnect switch of 1,500 feet from the main switch, and then the protective device for that wire is back at the main, it's going to take a lot more time for a fault at the disconnect switch to clear if the protective device 1,500 feet away has to operate. So your fault current may be lower because of the impedance of that wire, but the time element is going to be greater, so your arc flash level will be greater. So that's something to think about as well. And then the distance to the worker, of course, has a big impact on what this level will be. The distance is your friend when it comes to any kind of arc flash stuff. So these are some important things and important distinctions to think about. My smiley faces are in the way here. But this is an example. So if you're working right here on this part of the main, you're feeding through the transformer, and then you've got these switches, but you're going to have probably some fuse disconnects in there. So it depends on where it is in there as to how serious it'll be. All right, let's just go through a typical arc flash analysis of a plant. And so this is a real study that was done. And this particular plant, it was an older plant, and they replaced the switchgear, and it was old 4,000 amp switchgear. They replaced it with 1,600 amp switchgear, and then they kept the same old transformer outside. So with that same old transformer and the low impedance on that transformer, we ended up with an arc flash boundary of 115 inches, and which resulted in 76 calories per square centimeter at 18 inches. So that's a pretty significant arc flash event that would occur in that. If it did occur, it would be significant. So we'd have to really consider what that is. Now, downstream from the main, where you have the main distribution panel, it would be lower, but you still would have to protect for the entire plant, the entire panel at that same high level. So in other words, this is not enough. You can't, a category 4 is just not enough to be able to do that. Now downstream from that disconnect, so as we're going from here, going downstream, we'll go into another panel. And so at this point, down in this area, we're being protected from this area. So that will then be at this level, at the 55 inches or 7.6 calories. Downstream from that, it's going to shrink up quite a bit, but you'll see the level of protection that needs to happen. You have to have balaclava hood and at least 7.6 calories of clothing in a field. Downstream from that, we're down to 2.2 calories. And generally, 3 levels down from the main is going to be relatively low. And I think I have a note on that regard. But this is 2.2, so it's over still the 1.2 calories for our working distance. So we need to go with a shield as well with at least 2.2 calories of clothing. Downstream from this, it's going to be very low, and you'll probably have a very small arc flash. So that won't require any particular clothing other than rubber gloves and leather protectors. In the 2018 NFPA 70E, it did state that rubber gloves with leather protectors are adequate protection for arc flash, which is a good thing. It didn't state what their ratings are, but they do exceed 40 calories typically, so they're able to just make that statement based on tests that have been done. So, and that's the other thing to think about. These labels and this study, it gives you information of what the arc flash level would be at 18 inches, but it doesn't tell you what it is at 2 inches. So where the fingers are, even though the it's only 0.5 calories at 18 inches, at the point of where the contact was, where the fingers are, it was enough in this case to cause a second-degree burn. So it exceeded 1.2 calories, and that's something to think about. But the rubber gloves should have been used to do that particular job, which would then provide protection for arc flash as well. So as I mentioned, 3 or 4 levels down from the main disconnect is usually under 1.2 calories, just as a rule of thumb. Here's a couple of things that it's important to think about. So on the right, we have a time current curve, and this shows various devices and how they're supposed to be coordinated. There's overlap, and these would have to be coordinated by the engineer. And when you go into the EasyPower software, you can actually make adjustments according to what would be coordinated, and that would give you the new settings, or if applicable. On the left side, we have a new note from table 130.7 C15A, where in the past the tables just required that you have to go within a certain fault current, a certain clearing time in order to use the table. They never really told you or correlated anything to this, so now they do. current limiting fuses 0.5, molded case breakers 1.5 cycles, and so forth down the line. This is where you start to get into the maintenance requirements, because if you don't maintain these things, how can you say a molded case breaker is going to operate in 1.5 cycles if it hasn't even been exercised in 20 years? So it's important to look at NFPA 70B and look at it, or the manufacturer first off, and get the recommended maintenance and make sure you do that maintenance so that they do operate within the time current curve specified by the manufacturer. One thing to note too is the OSHA rule on short circuit studies and coordination studies is 1910-303B5. So OSHA actually requires that we do a short circuit study and a coordination study for our systems. Now the problem is we do that when our plants are new. So an engineer will be hired to design the electrical systems based on our specs and our loads and so forth, and they will contact the utility and they'll find out what the available fault current is and some other data, and then come up with the ratings of the equipment that according to the short circuit study. So they may say, okay, we need to get 65,000 amp rated switchgear and panels and so forth, and whatever they're going to need to do. Now that might have been in 1965, and in 1965 that worked, but as we're now doing these arc flash studies, we're finding that the available fault current is not what it was in 1965, and a lot of the equipment out there is over dutied, meaning it's not rated for the fault current that it should be. So so you can go back to OSHA if you need some information as to why you need to do it. There's some ammunition for you at 1910-303B5. Just a small paragraph. Equipment construction and installation will ensure safe performance under conditions of proper use and maintenance. And this is 1910-307G4. So there's some OSHA requirements related to maintenance. So it goes a little beyond. I mean, 70E and 70B are guidance documents. They don't tell you what you have to do. They tell you how to do it. The OSHA requirements are the regulations that tell you have to do it, but they don't tell you how to do it. And that's why you need to use kind of both in order to be able to figure out which is which. This is after a 480 volt arc flash. It was estimated to be over 10 calories. And you can notice that there's the rubber gloves actually held up pretty good where the leather protector was. So that you can see the leather protector was damaged pretty badly. But notice this. This is an interesting thing right here. OSHA actually says that you can wear your jewelry, your rings, your watches, and all that as long as you make them non-conductive. So that's an exception to taking them off. Unfortunately, what happens is that wasn't because of a pinhole. That was because of the ionization of the air on this 40 volt arc flash that caused that ring to heat up and melt the rubber. So this guy had a real significant burn on his ring finger from that event. And so my thought is take all the jewelry off. Don't be wearing anything metal, no metal rim glasses, anything like that, that in an arc flash event would superheat and cause significant burns. It's not going to be a fatality, but it's a burn that's unnecessary if the jewelry had been taken off. So that's just a little sidebar on that one. So you can see this person was standing to the side, and they ended up with a burn on their shirt. It held up for the most part. It did breach a little bit in this area right here. So that's why it's estimated to be over 10 calories on this 8.4 calorie shirt. So a qualified person has to do an assessment. They have to demonstrate their knowledge and skills in construction operation and understand the hazards. So he's going to look at this and he's going to determine what's his restricted approach boundary, and that's the boundary you have to be qualified and protected to go within. He's going to determine what his shock boundary is for unqualified people, and that's where he's going to have to barricade at a minimum. And then if the arc flash boundary exceeds that, then he would actually place his boundary, his barrier back out at whatever that flash boundary is, and that may be calculated or use of tables. And I'm going to talk about the differences between the calculations and the tables in a bit. This is not new to OSHA or NFPA, but it has had a lot of emphasis placed on it in the past two versions, 15 and 2018, and NFPA 70E. And OSHA has actually adopted some risk assessment and task-related training associated with it as well, with the onset of the newest 269 classes for the electrical standards for utilities. I expect that's going to take place, and actually most of NFPA will probably be adopted in the newest subpart S when that gets promulgated, which will probably be a number of years away. So this decision-making process says workers shall be able to, and now shall is subjective, depending, because it's an NFPA document, it depends on states and who adopts it and if it becomes law or not, or just more of a suggestion as a consensus standard. So we have to be able to perform the job safely, identify electrical hazards, and then we have to assess the associated risk. So that's relatively new to a lot of electricians. We've always been taught to identify what the hazard is, what are exposed parts, what are our nominal voltages, and how far away do we have to stay away from it. But now it's assessing the risk, and that has a whole different slant to it than what we've done in the past. And then we have to determine the risk control method from the hierarchy of control. This is good stuff, and it should be part of all the training programs that electrical workers get because it's important to identify these things. I always tell folks when I'm doing a class to just plant your feet. Just stop, plant your feet for 30 seconds. Look around, identify the hazards, identify the risks, and in that little bit of time, you'll provide the safe work practices you need to get home safely to your families. And that's, so I just say, give your family 30 seconds of your time before you start work, and that's an important thing to do. So, and then also in that time, ask what if this happens? What if that happens? What if that happens? And that's part of the risk assessment. So, so first thing we're going to do is we're going to look at what is the severity with that what if. We're going to say, if that does happen, is it going to be minor, moderate, serious, or catastrophic? And so that's the determination you're going to do and make based on some of the stuff we've already talked about. Are you downstream from a fuse, a breaker? What's the condition of maintenance and all that kind of stuff, and what's the available fault current and everything that we talked about. Once you determine the hazard level or the severity, then determine the probability, and that gets into how new is it, how long has it been since it's been maintained, and all of that other stuff. So we're gonna talk more about that in a moment. Everyone should have an electrical written safety program. You've got to implement it and document over for electrical safety. And in that, in 2015, they added the requirement that the conditions of maintenance has to be part of that written program. So there again, if you're following NFPA 70E, then maintenance is a requirement. If you're following OSHA, then you're still conditions of maintenance are a requirement based on the OSHA standards as well. So maintenance is something that is part of the regulations and the standards as we go forward. So here's a couple of scenarios. We have one on the left, 1964 switchgear, 1600 amps. One on the right, 2004 switchgear, 1600 amps. This gives you an idea of the differences in the risk level when you're doing some work on stuff. So this has no record of maintenance on the left, 1964, that's 50 years old, no record of maintenance. Fed by a 2000 kVA transformer, just like the other one, fed by a 2000 kVA transformer. But this is an older one, so it's got a 3.6% impedance. The one on the right is 1600 amp switchgear, fed by a 2000 kVA with a 5.5% impedance. Now, what that's going to do, the lower impedance is going to make higher fault current. So your risk level in that regard is going to be more severe. So you might go from a serious to a catastrophic event if it should fail. And so that's part of it. And now the likelihood or the probability is going to be probably in the occasional or probable or maybe even frequent scale, but it's going to be one of the red zones on the left. So this is in red, and then on the right, this may be more serious, and it might be in a remote or improbable. So we're going to say it's the orange level. So that's what we want to think about when we're doing our risk assessment, one versus the other. This is very, very different work, even though they're both 1600 amp switchgears coming from 2000 kVA transformers. Very different risk level. And this is part of what qualified people need to know. And then, it also gets into the maintenance of things. So here's a little on administrative law. This is what OSHA will cite you regarding the ARC/PPE requirements, because in 1910, 132 is the subpart I requirements for employers that they're supposed to assess the workplace and determine hazards, and the PPE requirements associated with those hazards. There's nothing in subpart I about arc flash clothing. It's got hand and foot protection and eye protection and hearing protection and respiratory protection and all that in there, but it doesn't have anything about arc flash. But in OSHA 1910-335, this is the electrical standard, and it says employees working in areas where there are electrical hazards, doesn't state what kind of hazards, shall be provided with and shall use protective equipment that is designed and constructed for the specific part of the body to be protected and for the work to be performed. It doesn't say what kind of work. So this is what they're actually citing now for not having arc flash clothing that's adequate for the job. Generally, they will use this if they identify somebody working on something energized and not having any kind of protection. They would go to this standard. The equipment all has to be in safe and reliable conditions, just like all of the PPE that we have to use. And we have to do a visual inspection and then lab test gloves and things like that. But there is no requirements for inspection other than our own inspection of our clothing and so forth. But there's no lab test requirements for clothing and shields and stuff at this time. The clothing is important that we know that the clothing has to have an ATPV or EBT in calories per square centimeters. So our thermal performance value is what you usually see on your arc flash clothing. If it says FR clothing and it may have a standard listed, an NFPA standard listed, that means it's a fire resistant clothing. It is not rated for arc flash. So don't get into someone selling you fire resistant clothing when it's really not arc rated and you need it for arc rating. So that's an important thing. Arc rated clothing is inherently fire resistant. So you can use that for both. FR, fire resistant clothing, is not typically arc rated. So it has to have a calorie per square centimeter rating on it in order to be considered arc rated clothing. So that's important. This is the table 15AA in the NFPA 70E standard, and it's your risk assessment table. So this is on the DC side of things, but it's got the same thing on the AC. So normal operation of a circuit breaker, contactor, or starter. I have also a picture in here that would be work on energized conductors and parts, including voltage testing. This just applying some protective cover on the bus work. This is what you'd have to follow. So do you need it or do you not need it? If all of the following for operating a circuit breaker or contactor, that's with all the doors closed, you don't need it if the equipment's installed properly, if it's maintained properly, doors are closed and secured, and covers are in place and secured, and there's no evidence of impending failure. If any of that is not true, then you would have to have arc-rated clothing just to operate a switch or a circuit breaker on the outside of things. So that's an important thing to think about. And this is the other table that would be used. I want you to think about this with regard to the first slide I had showed you with the arc flash, where it was 115-inch arc flash boundary and it was 76 calories per square centimeter. So think about this as we go forward. So if you look at the bottom, and you had that would have been in this kind of area. So 600 class switchgear, and based on that information, it would be a category 4, so you'd have to have a suit. Our class boundary is 20 feet. So does that cut it? Well, 115 inches is about 10, a little under 10 feet, so that our class boundary would be okay. But the 76 calories would be a problem because the 40 calorie suit would not cut it. And that's the difference between doing an R class analysis from an engineering standpoint versus doing using the tables. That's just one example. So my personal thought is that it's better to do an R class, a full analysis, than it is to do and go by the tables. The other thing is, if you talk to electricians out there, I'm going to say that probably 90% of them will not look at this data. They'll not examine that. They will see I'm downstream on a VFD, and so it's 30 cycles, or it's that high, and so that, and then what's your clearing time, or what's your available fault current, and they don't know. They're not getting the data that they should get to be able to know that they can use the tables. They're just blanketly saying, let's just use the tables. So a percentage of the time they'll be fine. Some of the time they'll be at overkill, but there are those times where it's just not going to do what it needs to do. So if you're using the tables and you're doing the things you should do by obtaining the clearing time and the fault current to make sure you're within the parameters of the tables, then you can go by this category. It used to be there was a category 0, which is now not applicable, and then here it's not applicable. The only difference between these two are one of them on the bottom has a shock hazard, so they have to wear a hard hat and rubber gloves. Up on the top, there's no shock hazard, so it's not a problem. Go to category 1, and you got a balaclava hood and 4-calorie clothing. Category 2, 8-calorie clothing and a balaclava hood. Category 3, 25 calorie, and category 4, 40 calorie. Most companies don't have two different types of suits. They just get the 40 calorie suit, and that's kind of takes care of everything. And I think in the future that's probably going to be something that you'll see change in NFPA 70E. I think that they'll probably go to a 3-category system and eliminate that need for the category 3 level. And when it comes to the engineering study, the difference is it doesn't state it's 4 or it's 5 or 2, it's 1. It just basically tells you what the calorie rating is, and you just have to exceed what that calorie rating is. And you can do that by layering. So there's some good things about having an R class study where if it's say 8.6 calories, you'd have to go to this level because it's over 8. And we don't want to necessarily put people in this kind of a suit when it's 8.2 calories, and they could have an 8.4 calorie coveralls and exceed what it needs to exceed and use that level. So there's some advantages to doing the engineering study. And this is some of the newer sections in 2018. So 1.2 to 12 calorie arc rated clothes are equal to or greater. So then you can layer up to that level and then even for over 12 calories, if the system is tested as a combination, pants, coveralls, and suit, you can layer those systems and actually get it to a higher level. And they will usually they'll be more than the addition of one versus the other. It'll actually be a significant increase because of the air in between. So that's a good thing about using an incident energy. And the other thing, for labels, you cannot put category, what used to be hazard risk categories, now R class PPE category, 1, 2, 3, and 4. So you can't put the category ratings anymore on the labels themselves. You can only have the calorie rating of whatever that exposure is, and then you have to exceed that level based on your training and the equipment that you're wearing. You can layer it as long as it's put together by a system. If you're using the same manufacturer, they probably have tested various shirts together, shirts and jackets, things like that, and they probably can provide you that information online. Most of the larger R-class clothing manufacturers can do that. This is a little different label than maybe you've seen, but we actually put danger on all of our labels, even if it's a low risk. It's got a 1.2 calorie. We'll still have danger. And I've been questioned by OSHA on this, and dropped it pretty quickly because I let them know that there's still a shock hazard. If the panel is open, there's still a shock hazard, and that's a dangerous condition. And they say they're okay, and they're fine with it. So we put danger on ours, and we put the ANSI symbols, and so we meet the ANSI 535 standards. We also put on our labels what the equipment is that it's fed by, so that we can know where we need to do our lockout tagout. And then we also put on our fault current, so that we know what the fault current is on that particular label, which is now an NEC requirement, which is adopted by many states as law for the state by statute. And then we just color code it with our different levels. So if this switch is up, if this label's up on a bus duct and they see it's an orange label before they even go up in the lift, they know what level of coding they need to have to do that work. So just a few things, but there's a lot of different labels out there, and it's there's some good and some that are minimal but compliant. Okay. All right, I'm going to go through a couple causal factors, or a few causal factors from equipment due to lack of maintenance. Also, poor communication between maintenance staff and production staff, that happens sometimes. And then sometimes it's just maintenance people just don't know. They don't understand, and so there's a human error that occurs. So if they don't fully understand construction and operation, are they actually doing the maintenance properly? And that's a big problem as well. So that's a part of being considered qualified. They must understand construction and operation and the hazards involved. We teach safety and the hazards involved. We don't teach the construction and operation because that's on every piece of equipment that they work on. So that's an important distinction for these folks as well. Sometimes static or spark discharge during maintenance of an intrinsically safe area. That's not very common, but it can happen certainly. There's some issues related to that, new OSHA requirements. If you do have a process that's being brought in, it has to be a third party or a qualified engineer has to study what the hazard level is related to the fumes or air contaminants that could be flammable or explosive. And they have to document the demarcation of that. So maybe a new paint booth or whatever it is. There must be documentation on what that demarcation is, and everything within that zone has to be intrinsically safe. And then there's studies that have to be done. And sometimes the training is an issue, and it's not adequately trained. This is an OSHA requirement. The path to ground from circuits, equipment, and enclosures must be permanent, continuous, and effective. So first off, you got to have an alternate path for current to go, number one. And number two, you need to have a good reference to ground for your operating device or your protective device to operate for a ground trip situation. If your grounds, like on the left, you have some grounding wires that are really in a connected to a bad piece of metal. It's a channel. It's not designed to be an electrical piece of equipment, and so it's corroded, and the resistance is going to be high. We want it to be less than 25 ohms, and typically, realistically, we'd like to even be less than that to be effective. And this is not there. This is probably in the thousands of ohms, and that's going to have an impact on your time current curves of your protective device, which is not going to be a good thing. Okay. So breaker fails. The breaker that was connected failed to trip because of this bad connection. Breakers, just to give you an idea of what's inside a breaker, there's a lot of moving parts inside of breakers, and if you never operate those, then there's some issues that you're going to come up with because the moving parts may not move the way that they're supposed to move. And so that's why these have to be operated from time to time. So this is just, again, lack of maintenance. Another thing to think about is torquing. There's every electrical connection should be torqued. Every electrician should have a torquing screwdriver and a torque wrench, and every connection when it's made should be torqued. Most of the time, what happens is they over torque them, and once they're over torqued, it's just as bad as under torquing, and it's going to cause friction from that compression of the strands, and it's going to cause heat from that increased impedance. Over duty breakers will fail or can fail, and they may not operate the way they're supposed to, or they may not operate, period. Excessive dust. If you have especially a high dust areas, your level of maintenance needs to go, and you got to step it up, and you want to make sure you have intrinsically safe stuff or dust-proof equipment and enclosures to keep the dust out of the electrical area. This is the torquing issue. So when you have bad connections, that's the kind of heat that you may have built up from that. And if you don't do, and by the way, infrared testing is a good thing to do as part of a maintenance program. Transformer oil. So transformer oil, you just don't let that sit there for 20 years and think everything's fine. There could be a buildup of carbon. There could be a small leak. There could be some oxygen in the oil that shouldn't be there. So there's periodic tests that should be done on the oil. Typically, it's once a year. So that's one thing to think about too. Underground cables, and they should be high pot tested or at least measured periodically to make sure there's no failures that occur. So it's just a maintenance guide for that. And there's forms on the NFPA 70B. I strongly suggest, if you don't have NFPA 70B, download it electronically. Then you can pull the forms right off the system and print them out and use them for your maintenance program, and it works out pretty well. This was a breaker that was racked in the on position. Now your system should not allow you to do that. It should dump that out when you're racking it in, but it didn't do that. They picked up load as they were racking it in and caused this failure. The good thing is that the guy on the suit on the right, the person wearing that, was only in the hospital for a week because he had the suit on. He did have some burns, but the suit did its job even though it failed. Loose connection caused this kind of thing. So when you think about something like this and what the effect is, say nobody got hurt or anything like that, this is outage time. This is not going to be an hour or a day or maybe in a week. This may be weeks and weeks of replacement, of getting switchgear replaced, and how much the productivity time is that going to affect, and the products, and it's going to be a tough thing to justify with the people up above. Grounding switch. This one, the interlock actually has failed, and what they did is they had several of these units side by side. They went and did some work in the morning, shut down the switch, and then in the afternoon they intended to do maintenance. So they got back in the afternoon, closed the grounding switch to another unit. It wasn't properly marked. So they have these little square things with a flag that you can stick with a little square magnet, and it just kind of tells you what you're working on when you have look-alike equipment, which is always a good idea. But it's also, if you go away and you're going to be doing something like that after lunch, have another job briefing to determine what happened and where you are. This is another one that failed. The actual switch failed itself, caused a flash, and blew the door off. The door went about 20 feet in this direction. The two guys working on it went about 20 feet in that direction. One was in the hospital for about a month. The other one was released within a day or two. All right, a little bit on due diligence, and we'll wrap it up. So first off, we want to take every precaution reasonable in the circumstances for the protection of the worker. So this is what due diligence means: reasonable, not everything that's in the world that could possibly happen. Everything that you think could happen, you need to address. So that's part of due diligence, and to secure the workers from risk to their safety, health, and welfare arising out of the or in connected with activities in their workplaces. So that's the safety part of it. The other part of it is, of course, what's going to happen to the equipment itself and what's your due diligence to protecting your products and clients. Negligence in a tort case. So first off, employers have to have the duty to prevent foreseeable harm. And the breach of duty results from acting irresponsibility under circumstances that breach the legal duty to avoid care, to avoid acts of omission. And then the damages or losses caused by harm as a result of the breach of duty. So this is where a tort case comes into play, and this is the premise of that. So here's a few different cases that occurred. So a California business paid $32 million in damages and claims. And I'm not going to read through this whole thing, but it just kind of gives you an idea of some things. It's an 18-story building and a prolonged arc. And then we have this one. It was $13.9 million. And if you look over at this section, plaintiff's lawyers allege that the accident was a result of a failure to perform routine maintenance. $13.9 million. Here's just a few more. $100,000 from a high dust area, and then $800,000 from a switch that could have been maintained, and a few more cases. 16.5 industrial. These are just some other ones that I pulled up off the site. I do some expert witness work on this kind of thing, so it's something that the ones that I work on, unfortunately, resulted in usually a fatality or serious injury, which is not fun to work on, but those are just the consequences that you have to deal with sometimes. These are some pros and cons of the electrical preventive maintenance program. So obviously the pros are reliability, reduce corporate risk, save money, longevity of equipment, safety for personnel, it's a big one, outage planning, on-time delivery. The cons are cost money, and this is stuff that people have to look at. What's it going to cost? What's the risk to the company? And the guys up on the top have to make that decision as is this worth the money or is it not? In my book, it's definitely worth the money because one event could take away 10 or 15 or 20 years of maintenance. So 70B just says, without a program, management assumes greater increased risk. This is how it's written in 70B, and that's an important thing to think about. A couple ways of engineering it out. Certainly performing regular maintenance certainly helps. If by remote operation of the equipment, if you can do it remotely, distance is your friend, as I mentioned, that's a good thing. The clearing time, you can reduce the clearing time by installing arc flash relays, which won't mess up the coordination because it's based on a flash. Install differential relays that work similar to a GFCI and take the power out very quickly. Adjust breaker settings, and it may be like a maintenance setting for temporary settings, or maybe you can still coordinate it and then bring the settings down. You can also put a faster blowing fuses or install fuses versus having breakers. Infrared analysis is always good to define things as a proactive approach rather than reactive. Arc flash rated equipment is a good thing also. It's very expensive, pricey, very heavy. So it's not something that you see very often in the area. Okay, just to wrap it up. So first off, hopefully we can determine the cause and effect of the arc flash incidences that occur out there, and it'll help us to determine what we need to do to prevent those. We can explain the difference of conducting an engineering study versus using the tables and some of the advantages of doing an engineering study. Talk about, and we discussed why maintenance is so important, so hopefully that's been covered. And the consequences from lack of maintenance, including extended outage and civil litigation. And then describe how to mitigate the hazards, which we just kind of covered that piece. So I guess I'm ready for questions, Jim, if you want to take that on.
Thank you, Lee. It's a very good job. And I do see one question. Let me kind of read it to you. The question is, energized work an engineer claims a 1960 style switchgear with no record of circuit breaker maintenance, categories dangerous and no PPE exists. What is your position on asking someone to be physically present in the arc flash zone? How's
I
that for
think
putting
that
you on the
that
spot?
has to be. Oh, that's not a problem. So that happens a lot. We get a situation where we've done a study, and like the one we pointed out, 74 calories or 76. How are you going to get in there to do some work on the bus? Maybe to, whatever, inspect it. You're not. So the answer is basically it's got to be shut down. You've got to call the utility and have them shut the power down. So you've got to take an outage. And that's a good time to think of other ways to mitigate the high arc flash level and maybe change out a transformer or do some things that you might be able to get that level down to a manageable level in the future. But you just don't go in things that are greater than 40 calories. I mean, they have 100-calorie suits, but the arc blast, when you get to those high levels, is not worth the risk. So my answer really is call utility and arrange for an outage.
Kurt had a follow-up question that said the engineer says as long as he's in place and not as long as covers are in place, this is not engineered work. So I think that's
Correct.
one we
Yeah.
can.
If
Yeah, we
covers
can.
are in place, yeah, that's fine.
Right.
That's a different thing. I was talking about if you take covers off
Right.
for whatever reason, you just don't do that when it's energized. So if covers are in place, and let's just say that you're going to operate a breaker with the covers in place, you do a risk assessment. What we've done in the past, where like the picture we had with the push button shutoffs on the Magnablast breaker or whatever the manufactured breaker is, we put a little rubber cover on a switch stick, and then an extendable switch stick, and we actually push that button from 6 feet away. And at 6 feet away, if something were to occur, they were under 20 calories, so it wasn't a problem.
Here's another question that's a little bit, excuse me, Lee, a little bit on the same line. It says, even if the equipment is shut down, how do you protect the worker while it's tested to ensure it's de-energized?
From a distance. So you that's one thing that you can use a proximity tester for. Just to, you have to check it at a known source first, and then carefully open the door or take the cover off and maintain as much distance as you can with the suit that you have. But you'll want to ask your engineer that did the study to tell you at what distance it goes down below 40 calories, so you can maintain that distance. If you can't maintain the distance, then you can always test it outside at the utility transformer, or have them test it when they de-energize for you. And then you can test it at that 480 volt level out there.
All right.
That can be done at a distance. It's a hinge cover.
Here's another one, and that was a very good answer. Thank you. Another one, the study is performed, but there's a visible lack of maintenance. Should you still label the equipment or force the owner to do the maintenance first?
Well, that's a really good question. and I don't think there's any forcing on anything. You can certainly make the suggestion. In our reports, we will say, this is based on, maintenance being done, blah, 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 and if it's not maintained properly, then all bets are off. We just can't go with that. We went to one place where the equipment had been underwater. That's a whole different ballgame, because now you can maintain that, but it's a whole different ballgame. So we had to, what they do is they step it up one level, and if it's already at a high level, then we just made sure we de-energize.
Okay. Any other questions we'll have to answer? Follow up via email. Lee, appreciate the support and the presentation. I think you did a great job, and the audience, I think, was very responsive.